Alright guys, so we're going to get started. There is one problem I want to do from, not specifically from the homework, but like one of the problems on the homework, because I think 3 of y'all have asked about it, is it gives you a graph of the parabola and tells you that the vertex is, we'll say, 2, 9, and then a point on the parabola, we'll say, is 4, 20. And it gives you kind of a setup like this here, and it wants you to write it in vertex form. Now, vertex form is our y equals a times x minus h squared plus k. Now, they already gave us the vertex here, in this case, 2, 9. And we can plug that in, x minus 2 squared plus 9. Now, the only thing we need to find is the value of a. And to do that, we're going to just take the point, 420, and plug it in. So we're saying y is 20 when x is 4. And we're going to solve this here. Now, one of the first things we can do is 4 minus 2 is going to be 2 squared plus 9. Now, at this point here, we can get the a by itself by subtracting 9, telling us 11 is equal to 2 squared is 4a. And last but not least, we would divide both sides by 4, telling us a is 11/4. And at this point here, we just have to plug this back in to the original problem, telling us that y is equal to 11/4 times x minus 2 squared plus 9. And that's all we're really needing to do for this here. We plug the vertex in, then plug the given point in to solve for a, and plug a back into the formula. Now, what we're looking at today is polynomial functions, finding zeros of polynomial functions, and in behavior multiplicity. So we're covering a few different things. Now, the first thing we're looking at is this here. Let n be a whole number and a sub n minus 1, and continuing on, be all real numbers. So we're just saying that any of these a sub n's are all real numbers. Now, we use the sub n just to denote that they could be different, they could be the same. They're just a number. And we have to use different subnotations because those values in front of the variables are not going to be the same. They could be the same, but they're not. Most likely, they're going to give us different values. Positive, negative, anything of the like. And n is just whatever power we're starting with. So if we said n was 2, we're talking about quadratics, because we'd have n squared, or it's not n squared, we'd have x squared, x to the first, and then a constant term. If we said n was 20, well, our starting one would be x to the 20th. And then we'd have an x to the 19th term. And then we would continue on down to x squared, x, and then our constant term. It's just so that we can classify any quadratic, or not any quadratic, any polynomial by just this here. Now, we're also going to need to classify what a polynomial is not. Now, I find it easier to classify what's not a polynomial than trying to classify everything that is, because there's a few key indicators. One, if x is inside of a radical at all, it's not going to be a polynomial function. Or if we have x to a fractional exponent. Because when we covered radicals, we talked about the fact that we can change from radical form to exponential form, because it's just a fraction. These are the same. X to the 1/2 is the same as the square root of x. These are the same thing. So we can't have either one of these here. One of the other things we cannot have is we cannot have x in a variable, because these would be considered exponential functions, not a polynomial function. We also cannot have x to negative exponents or x in the bottom of a fraction. Well, we know if x, or if an exponent is negative, we move it from the numerator to the denominator to make it positive. So it's just fractional. And the only other exception is that we cannot have two variables being multiplied together. X times y is not going to work. And these here really are the ones that we had. In Algebra 2, we wrote this out in kind of more of a word form and wrote them all out in what we had. But these here are the main indicators telling us that it's not a polynomial function. So if we look at these first two here, our first one, given the function negative 3x to the fifth plus the square root of 2 times x plus 1/2 x, is this a polynomial function? What would we say? Because the square root, it is there, but the variable is not contained in it. Because we have the square root of 2 times x. If it had been over just a little bit more, we had the square root of 2x, then yes, it would not be a polynomial function. But because the variable is not inside the radical, it is a polynomial function. Because we don't have negative exponents, we don't have two variables multiplied together, we don't have x inside of a radical, x does not have fractional exponents, x is not in an exponent, so this is a polynomial function. If we look at the next one, negative 3x to the fifth plus 2 square root of x plus 2 over x, is this a polynomial function? No. Because we have 2 in the bottom, we have x in the bottom of a fraction, and we have the square root of x. So this is just no. Questions on any of those here? Okay. All of this here, this next part is in behavior. And when we talk about in behavior, really we're talking about the function graph as it continues indefinitely in the positive and negative direction on the x-axis. If we continue expanding both directions for any polynomial function, they're going to do one of two things. They're either going to go up or they're going to go down. They're going to rise or they're going to fall. And they're going to do that in one of two directions. As x approaches infinity, as we're talking about the domain, the input values increase positively in the positive direction, or as x approaches negative infinity, as our input values increase towards negative infinity. What is the function doing? F of x, we're talking about the y values going to infinity, or f of x approaches negative infinity, as the y values approach positive infinity or negative infinity. Get bigger positively or get smaller negatively is the kind of notation. Now here are the four that we have. Even functions are going to go in the same direction. They're either both going to go up or they're both going to go down. They're either going to both rise as left and right, or they're going to fall left and right. And this here is all based off the degree. Because if the degree is even, they're both going to go up or they're both going to go down. If the degree is odd, they're going to go in opposite directions. It's going to either fall to the right and rise to the left, or rise to the left and fall to the right. They're going to go in opposite directions. And the direction that they go is really based off the leading coefficient. Leading coefficient, the number in front of the variable with the biggest exponent. Or if we're in sets of parentheses, it's just the number out front. Because if the leading coefficient's positive, they're both going to go up. They're going to rise to the left and right. If it's even and positive, it's going to rise to the left and to the right. If the leading coefficient is negative with an even degree, it's going to fall to the left and to the right. It's going to decrease. They're going to eventually go down to the left and to the right. Now, if the degree is odd and we have a positive leading coefficient, it's going to fall to the left and rise to the right. And if we have an odd degree and negative leading coefficient, it's going to rise to the left and fall to the right. So if we look at this first function here, the degree is odd because the biggest exponent is 5, x to the fifth. 5 is odd, so the leading coefficient, or the degree, is odd. Now the leading coefficient, number in front of this variable is -4. So our leading coefficient is negative. And we can look back at the chart. So if we have an odd degree, odd, and negative leading coefficient, it's going to rise to the left and fall to the right. So this here, so A rises to the left and falls to the right. Now if we're talking, because this again, this rise to the left, falls to the right, this is how the homework especially is going to want you to do it. Mathematically, what we would say is f of x approaches infinity as x approaches negative infinity. As our values of x, our inputs go to the left, we decrease, the y values are going to go up. And we'd also say f of x approaches negative infinity as x approaches infinity. As x goes to the right, the y values are going down, they're falling. So this is how mathematically we would write this. And I'll put that back up here in a second. Clear that out. Because we had -4x to the fifth plus 6x to the fourth, and then plus 2x cubed, yes? This is our function, and if we graph it, we do see going to the left, it's going up, it rises, and going to the right, it falls, it goes down. Any other questions on A? We feel comfortable with A, yes? Now the degree with B would be what? Is it actually in standard form? Is it multiplied out? No. So we can't grab the biggest exponent with it. But we do know that if I multiplied it all the way out, this x here and this x here will be attached to those exponents. We're going to have to multiply the 2x minus 3 by itself how many times? 3 times. So that 2x is going to end up multiplying it by itself 3 times. This x is going to end up multiplying by itself twice. And then we have another x here, yes? So that's 3 here, 2 here, and 1, which would give us a degree of 6. We can add those together because they'll end up being multiplied together, and it gives us a degree of 6, which is even. Leading coefficient is normally going to be the number out front. So here we have 1/4, but the 1/4 is positive. So if you have even and positive, looking back at the chart, degree is even, positive, it's going up in both directions. So we can say it rises to the left and rises to the right. So the second function here rises to the left and rises to the right. It's going up in both directions. Now again, if we wanted to write this mathematically, we would say f of x approaches infinity as x approaches negative infinity. We'd say f of x approaches infinity as x approaches negative infinity. As we plug smaller and smaller values of x into the function, it's going to continue to go up. And as we plug, and then f of x approaches infinity as x approaches infinity, as we plug in bigger and bigger values of x, the function's y values will continue to increase. I can also come over here into the graphing calculator and say fraction 1/4 x times 2x minus 3 to the third power times x, what is it, plus 1 plus 4 squared. We can hit graph. And we can see that it is going to end up going up. It's a funky looking graph. We can zoom out, but they're going to end up going up. We can say zoom fit. We'll try to get it so it looks like it should. And we can see here it goes up and up. So it's rising to the left and to the right. Any questions on end behavior? And that's really all end behavior is. Now, end behavior is helpful, especially when we're looking at functions, because if we know it's cubic or we know it's an odd degree, we know the function's endpoints are going to be in opposite directions. If we know the degree of the function's even, we know it should go in the same direction. They should both go up or both go down. Any questions on any of this here so far? Now we look at the next one, determining the zeros, finding the zeros defined by each function. And when we find zeros, we're just trying to see where it crosses the x-axis. What value of x will make this function be 0? So we call it a 0. Or really, what value of f of x, if we replaced f of x with 0, would work? Now there's different ways we can go about doing this. But one way, cubed plus x squared minus 9x minus 9. I can graph it. I can graph the function. And we see that it does cross at 3 nice places. One of the places is -3, because again, we're seeing what value of x will make the y value be 0. So we have -3, -1, and 3. Those are our 3 solutions. And again, the degree, so here the degree is 3. Whatever the degree is will equal the number of solutions, including repeated solutions. So graphing is one way to find it. The other way we can do this is factoring. Now we would factor by something called grouping, because if we have an even number of terms, or we can put them into even groups, we use grouping. And with 4 terms, we can use grouping, or I call it greatest common factor twice. So if we look at the first 2 terms, x squared and x, both of these have a greatest common factor of x squared. Because if I pull x squared out of x cubed, we're left with 1x. If I take x squared away from x squared, we're left with 1. Any questions on this so far? Now, what's the greatest common factor between -9x and -9? Well, -9. And if we take -9 and away from -9x, we're left with x. And -9 factored out of -9 is plus 1. Now, after doing this, do both of these 2 terms have something in common? Well, yeah, they have the x plus 1. So what we can do is we can factor it out of both terms. And if we factor it away from our first term, we're left with x squared. If we factor it away from our second term, we're left with minus 9. And whenever we have two things multiplied together to equal 0, one of them must be 0. And solving the x plus 1 is kind of nice. It tells us x is equal to negative 1, which again, we already found it with graphing. X squared plus 9. We would add 9 to both sides, telling us x squared is equal to 9. Then we would square root both sides, telling us x is equal to plus or minus 3. And again, one thing to remember, whenever we square root both sides, we have to add the plus or minus. If we square, put both sides to the second power, we don't need it. It's only if we square root both sides. Any questions on this so far? Not too bad. Let's look at the other one. 4x cubed minus 4x squared. 4x cubed minus 4x squared. So here's plus 25x minus 25, yes? Okay, it was the other way. Thank you. Minus plus graph. We do see a nice value, because if I go second graph, at 1, we do have a 0, yes? Now, we will have something here, and we'll talk about it towards the end of the lesson, something called the intermediate value theorem. Because if we're talking about something crossing the x-axis, numbers above the x-axis, the y-values are positive. The numbers below the x-axis are negative, yes? So the intermediate value theorem states that if between two x's, especially on this here where we have whole number integers for the x's, if the y-values go from positive to negative or negative to positive, there must be a 0 between the two. So if we look at this here, x is negative 3, we have a y-value of negative 4. It's below the x-axis. When we go to negative 2 for x, the y-value is now positive 27. Well, the only way for the y-value to go from negative to positive is if it crosses the x-axis. So according to the intermediate value theorem, which we will have a little bit later, it states that between the x values of negative 3 and negative 2, there must be a 0. The only way that we can get from positive y to a negative y or negative y to positive y is if it crosses the x-axis. So we have a 0 between negative 3 and negative 2. Well, all the values are positive. And at 1, we do hit 0. It hits the x-axis, yes? And we see the next y value is negative. But then the one after it is positive. So it's got to come back across. Which helps us a little bit because we do know x is 1. But do we know what the others are? No. So this one here, we do have to factor it. And since we do have 4 terms, we can use factoring by grouping. I always group the first 2 and last 2. The greatest common factor between 4x cubed and 4x squared is 4x squared. And we can pull it out. If I factor 4x squared out of 4x cubed, we're left with x. 4x squared out of negative 4x squared is negative 1. So again, that's what we're kind of doing. We're factoring something out so we get 2 parentheses that are the Same. Yes? So really we want to factor something out of negative 25x and 25 and get what's left over to be what? X minus 1, yes? Now if we factor a 25 out, well, factoring 25 out of negative 25x give us a positive x. Well, no, we got to factor out a negative. We need to take the negative 25 out of the negative 25x to get a positive x because we need these to be the same. Well, the only way to get it to go from positive 25 to negative 1 is if I pull out a negative 25. Now they both have a greatest common factor of x minus 1. And what that leaves us with is 4x squared minus 25. And again, because we have two things multiplied together to equal 0, one of them is going to be 0. Good. Now, for the first one here, we can add 1, x is equal to 1. This one we already knew. The graphing calculator told us it. The other two that we need are going to come from our 4x squared minus 25. Now, the first thing we can do is add 25 to both sides. Telling us that 4x squared is equal to 25. Now, x squared is not by itself, so we're going to divide both sides by 4. Telling us x squared is equal to 25 over 4. And last but not least, we'll square root both sides. Telling us x is equal to, I'll scroll down just a little bit, well, plus or minus. Luckily, we can take the square root of the top and bottom of this fraction because the numerator is 25. Well, the square root of 25 is 5. Square root of 4 is 2. So our other two answers are plus or minus 5/2. And if we look back at the graphing calculator, that would line up where they were at 5/2 and negative 5/2. Now, it seems odd why we did this method for solving both of these here, but because we got 4x squared minus 25, we don't have a middle term. We're not having to factor to get it down. It's our square root method, get x squared by itself and then square root both sides. The other methods are using the quadratic formula, and most likely, especially next chapter, we'll use that to solve some quadratics. Any questions on any of these here? Any questions on anything we've done so far? Determine the zeros of this function. There is one zero we can find without doing any calculations whatsoever. Looking at that function, is there a constant term? So what's one of the zeros have to be? Because if I plug 0 into every single x, negative x cubed will be 0. 8x squared will be 0. And negative 16x is 0. Whenever they don't give me a constant term, it's kind of nice because it's telling me that spot 0 is a solution. And if whatever the power is, it'll also tell me that as well. So we know 0 is one of them. Now we could graph it. Negative x to the third. So we have this here, we can hit graph. Surprise, surprise, we do have it crossing at 0, 0, at the origin, yes? And we do have another 0 at 4. And we have these two spots here. But how many zeros did we say we should have? Because it's equal to the degree, so we should have 3, yes? Now, we should have. But looking at the graph, at 4, does it actually cross it? No, it hits the graph and goes the other way, yes? Now, I'm going to jump ahead because I do want to emphasize this with this graph. We'll look at that one there. If a 0 has an odd multiplicity, then the graph crosses the x-axis at that point. Odd multiplicity. In odd multiplicity, what that's stating is that the number of zeros at that point is odd. Normally, that just means 1. But we could also have 3 zeros at that point, or 5, or 7, or 9. It's just an odd number if it crosses. However, if the number of zeros is an even multiplicity, then the graph touches the x-axis and turns back. It does not cross. It doesn't cross it. So let's look back at the graph. So if it does not cross when x is 4, how many solutions should we have there? An even number, yes? So it could be 2, it could be 4, it could be 6, it could be 8. It's just an even number of times, yes? But it's not going to be 6. Since the degree is 3, we only have 3 solutions, yes? We know one of them's 0, the second one's 4, so the third one has to be 4. There's only 2 of them. We only have 3 solutions. 2 of them are 4, 1 of them is 0. And that's it. Questions on this here? Well, we were able to graph this and get this done. We could have factored out a negative x and then factored it from there. Or we can do this here. Questions on any of this so far? Let's solve this one here. Now this one here, is it in factored form? Yeah, it's all parentheses, yes? We could graph this. You could plug this into the graphing calculator, graph it, and then see where the zeros are. But what we have here is 5x times x plus 4 times x minus 12 squared times x minus 11, yes? Whenever we have one or more things multiplied together to equal 0, one of them must be 0, yes? So we're saying that 5x is 0. We're saying that x plus 4 is 0. We're saying that x minus 12 is 0. But how many times do we actually have x minus 12? Twice. It's squared. So this is really, we can say twice. And we also have that x minus 11 is 0. Now, if I wanted to, I could have rewritten x minus 12 again. But am I going to get a different answer from each one of those x minus 12s? No, there's no reason to put it more than once. And out of all of them, this one's the nicest. 5 times x is equal to 0. That's the only thing I can multiply 5 by and get 0. 0. X plus 4, we would minus 4. So x is equal to negative 4. Our next one, we would add 12 to both sides, telling us x is equal to 12. And lastly, we would add 11 to both sides, telling us x is equal to 11. We have 5 zeros. We have x is equal to 0, negative 4, 12, and 11. But we would say that x is equal to 12 has a multiplicity of 2. It appears twice. We have 2 zeros at that location. But that's it. If it's already written in factored form, set each one of them equal to 0 and solve. Questions on this here? Now, if one of the exponents had been, say, 3, then there had been 3 zeros at that point. Questions on any of this here? Determine the zeros in multiplicities. So the top one, 1/10 x minus 4 squared and 2x plus 5 cubed. So we do have 5 zeros. Because we have 2 from the first set of parentheses, we have 3 from the second, which gives us a total of 5. And we can set both of those equal to 0. Now with the x minus 4, we would just add 4, telling us x is equal to 4. Solved. The other one, we would subtract 5 first, telling us 2x is equal to -5. Then we would divide by 2, telling us x is equal to -5/2. Now at 4, we have a multiplicity of 2 because the exponent is 2. We have 2 zeros there. The multiplicity of x equals -5/2 is 3, because we do have the 3 here. I could go about graphing this. 1/10 we can say is 0.1 times x minus 4 squared times 2x plus 5 to the third graph. And our -2/5, it does cross. At 4, it does intersect that, and if we look at the table, we do get that 0, but it is increasing at such a steep was what I was looking for, rate. It's kind of hard to see on the graph, but we do have these intersections. Questions on this here? X to the 4th minus 2x squared. Well, we can just grab this here, say x to the 4th minus 2x squared, graph. Well, we do have a spot where we have an even multiplicity and 2 spots where we have an odd multiplicity. Unfortunately, two of them, 2x squared, aren't showing up on the graphing calculator. Now looking at this here, we do know one of the sets of zeros is going to be, well, 0, yes? Because we don't have a constant term. What's the variable with, what is the smallest exponent attached to a variable? 2, yes? So that tells me one thing specifically. It tells me 0 is going to show up twice. Whichever one has the smallest exponent is how many times 0 shows up. It also means I can factor out an x squared from both terms. Because if I factor x squared out of x to the 4th, we're left with x squared minus 2. We have more than one thing multiplied together to equal 0, yes? So one of them must be 0. I'm going to look at x squared equals 0 here in a minute. We can do the other one here, x squared minus 2. Since there is no middle term, we're going to get x squared by itself. X squared equals 2. And at this point here, we can square root both sides, telling us x is equal to plus or minus. Can we take the square root of 2 nicely? No. So two of our solutions are positive negative square root of 2. Now x squared equals 0. Well, that's the same as saying x times x equals 0, yes? Two things multiplied together equal 0. One of them must be 0. We really could have taken the square root of both sides and got x equals plus or minus 0. There is no positive or negative 0, so it's just 0. But it's also, I did it this way to show that there is an even multiplicity there. If it had been x cubed equals 0, we'd have 3 zeros. 0, 0, and 0. Questions on this here? Questions on anything we've done so far? Now, intermediate value theorem and one other theorem is all we have left. I know the bell's going to ring soon. But intermediate value theorem, we kind of already covered it. This here is the formal definition for a polynomial function for a less than b. We have two x values on the x-axis. We'll call a and b, and this is the origin at 0, 0. If a is less than b, and f of a is down here, and f of b is up here, opposite signs, then there's at least one 0 between a and b. That's all it's saying. If the y values change from positive to negative or negative to positive between two x values, then there's going to be an intersection between those values. That's all the intermediate value theorem is. Does that make sense? Now, we can expand on that and essentially create this distance between these 2 points smaller and smaller until we close in on what the x value is, or we can do other methods. No, we're not going to worry about that there. Now this here, the last thing, turning points. The number of turning points, the number of times the graph changes from decreasing to increasing or increasing to decreasing is 1 less than a degree. So a quadratic, the degree is 2, so it'll have 1 turning point. U-shaped graph. This way or this way. And we say at most, this is the most they could have. So a quartic, degree is 4, we should have 3 turning points. This here is a quartic. This here is also a quartic. U-shaped graph. Because again, it says it has at most n minus 1 turning points. So it could have 2 turning points or it could have 1. It doesn't have to stay that way. Kind of questions on this here, it kind of makes sense, yes? And that's what we have. Now, the last thing I'm going to talk about, and this is kind of going above and beyond, if in 3 dimensions we do have turning points, but we don't call them turning points, especially if it's increasing and decreasing at the same time. We have a meeting of those two. Kind of looks like a saddle, doesn't it? So they're actually called saddle points, where it's increasing and decreasing. That point is a saddle point, because incidentally, it does look like a saddle. But that is it. Homework